Good. So welcome to our Tuesday lunchtime plenary session. I am Catherine Chauvel. I'm the president of the European Association of Geochemistry. And today I will present the remainder of the EAG Awards. The first one is the Friedrich Houtermans Award that recognizes exceptional contribution made to geochemistry by scientists who are within 12 years of the start of their PhD. This award could not be given to the recipient in the past 3 years. So we will start with the 2021 Houtermans Award, was awarded to Paolo Sossi from ETH Zurich. Paolo has Paolo has made important contribution to isotope geochemistry and experimental geochemistry applied to understanding early solar irradiation, planet formation, and differentiation, and quantifying the fractionation of metal isotopes during planetary evaporation and core formation. Paolo, welcome on the stage. Now we move on to the 2022 Houtermans Award, and I wish to present it to Raffaella De Micheli from Curtin University. Raffaella has made important contribution to fundamental geochemistry by applying both ab initio quantum mechanical techniques and force field-based molecular dynamics to understanding the nucleation and surface geochemistry of biominerals, such as calcium carbonate and calcium phosphate. I'd like Raffaella to come on the stage. Oops. Now the third and last Houtermans Award. This is the 2023 Houtermans Award. So I will present it to Ming Tang from Peking University. Ming is particularly recognized for forging new paths, thinking in new ways about all problems, and having a significant impact on our understanding of Earth, particularly the evolution of continental crust. He's also a kind-hearted and patient mentor who inspires those around him. So I welcome Ming Tang on the stage. Okay, now so we move to the Science Innovation Award, and we'll start with the 2020 Science Innovation Award, named after Vernon Stum. I present it to Kevin Rosso from the Pacific Northwest National Laboratory. Kevin has successfully recognized the behavior and function of the electronic band structure, band bending, and the potential charge gradient built up in semiconducting minerals. That's a program. Come on the stage. The 2021 Science Innovation Award, named after Ted Ringwood, is now going to be presented to Fabrice Gaillard from the Institute of Earth Sciences at Orléans in France. Fabrice has made pioneering contribution to the experimental physics of MELS, and in using such physics to describe and understand the evolution of major Earth and planetary reservoirs. More specifically, he is awarded for his creative and impactful research on electrical conductivity, redox properties, and volatile in magmas. Fabrice, are you there? And now the 2023 Science Innovation Award. It's been named after Nicholas Shackleton, and I will present it today to Rose Rickaby from the University of Oxford. Rose is a world leader in developing novel proxies for marine carbonate to reconstruct climate and, more generally, Earth's environment over geological time. Her research has informed us about the co-evolution of the geosphere and biosphere. So I welcome Rose to come now on the stage. Okay, so now I'd like Phoebe, Sumit, and Catherine to come, please. So Sumit, you have a few words to say? You have a few words to say?
No, I just wanted to. You have the text, right?
Okay, just take the certificate.
I'll just take that.
Yeah, take that. You have to submit.
That's you.
I don't have. Oh, sorry, I missed it. Excuse me, I missed it. I missed something. Yeah, so I now invite Sumit Jakrovsky, President of the Geochemical Society, as well as Catherine Jandel, who is standing here, co-chair of the Goldschmidt conference, to join me to the presentation of the next honor, the Gas Lectureship Award, bestowed jointly by the two societies. This honor recognizes outstanding contribution to geochemistry by a mid-career scientist. Paul Werner Gast was the first Goldschmidt medalist in 1972, who pioneered the study of the rarest elements. So we're delighted to present this award to Phoebe Lamb from the University of California, Santa Cruz. Sorry, this is what I forgot to say.
So, good morning. My job now is to introduce you, and I have the pleasure to introduce you Phoebe Lamb. Phoebe is a marine particle lover. But what she's doing with the particle analysis are major scientific contributions, as you will see. The first thing is that you must realize that tracking marine particles is incredibly challenging. Indeed, their abundance in seawater is around 10 micrograms per liter. Thus, you have to filter 100 of seawater, of 10 liters, of seawater to get 1 milligram of material, while 1 milliliter of seawater brings 35 milligrams of salt. And 1 milligram of material, 35 milligrams of salt, if it dries on the same filter. This is an unfair fight. Meanwhile, the particles are the only way to transport solid material from the surface to the sediment. In other words, they are essential for the carbon sequestration in the deep ocean, which is a major climate issue. So we have to measure these particles. Phoebe Lam overcame all the sampling and analytical challenges. She was critical in designing a major technological advancement that improved the collection of marine particles, and then she was able to collect enough material to conduct breakthrough researches. Phoebe is today a reference for the quantification of coastal sources of trace metal or the export from the surface ocean of particulate organic carbon and trace metals. She has also played a critical role both in the observation but also modeling of the distribution of naturally occurring radionuclides that are used to quantify the rates of supply and cycling of trace metal and major sedimentary phases. As a result, Phoebe has emerged as a leader in the field of marine geochemistry. Major international recognition. In 2011, she became the youngest member to be elected to the International GEOTRACES Scientific Steering Committee, and she rapidly was elected as co-chair of this program. Last but not least, she is an excellent speaker, so it's time for me to let her seduce you with the shy, discreet marine particle venture. Phoebe, I welcome you.
Hi, everyone. Thank you so much for coming, and thank you so much, Catherine, for that lovely introduction. It is due to people like you and mentors that have supported me along the way that I am here. So I am a chemical oceanographer, as Catherine mentioned. For those of you who aren't chemical oceanographers, what that means is that I study the distribution of chemicals in the ocean, in my case, the chemistry of particles in the ocean, to understand important ocean processes. One of the reasons I like Goldschmidt as a conference is that it attracts the chemical oceanography community, but it also attracts the synchrotron community. And I'll show you a little bit about some of the synchrotron techniques that we're using to understand some molecular processes that have implications for a much greater scale. So I hope to be telling you about 15 orders of magnitude from the nanoscale to thousands of kilometers, mostly focusing on the thousands of kilometers, but also coming down, all the way down to the bottom. None of this would have been possible without funding support, without programmatic support, without my mentors, without students in my lab, postdocs in my lab, and many, many collaborators. So I won't name them all, but some of them are listed here. And of course, thank you to the Geochemical Society and the European Geochemistry Association for recognizing this, my work. Okay, so the story that I'm going to tell might start in 1954. This is when Ed Goldberg wrote a paper called Marine Geochemistry, Chemical Scavengers of the Sea. And so I've highlighted this one part. Actually, let me just turn on the laser pointer. Whoops. Nope. Back. Okay. I've highlighted the part that I'd like you to look at. So he wrote that the ability of hydrated oxides of manganese and iron to adsorb ions from solution is considered blah, 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 blah. Most importantly, he might have popularized this term scavenging, and it's a term that chemical oceanographers use all the time to describe the removal of trace elements in solution by the adsorption of trace metals onto a particle surface and the removal of particles from solution by sinking. People not chemical oceanographers are often confused what scavenging is, but that's what it is, and that's what I'll talk about from now on. The geochemists might just know this as adsorption. So I'll talk about it as scavenging. So he recognized the importance of hydrated oxides of manganese and iron. It was well known already to be really important removal of trace elements in industry, in industrial purposes, and industrial applications, and he surmised that it must also be important in the ocean, but the techniques weren't there in order to actually test this for sure. Another perhaps origin of this story might be 1977, Carl Tarikian in an address to the Geochemical Society, so quite relevant for this, talked about the great particle conspiracy. And so he wrote a paper to summarize his address called The Fate of Metals in the Ocean, and he asked, why are the oceans so depleted in trace metals? And he writes here, the secret lies in the role particles play as the sequestering agents for reactive elements during every step of the transport process from continent to ocean floor. The great particle conspiracy is active from land to sea to dominate the behavior of the dissolved species. So these two geochemists, decades ago, were prescient in identifying the important role of particles and of oxides of iron and manganese in the removal of trace elements from seawater. But as I said, the techniques weren't there to actually measure it directly, for sure. So it's really only in the last 10 to 15 years in the GEOTRACES era that we've collected enough quantity and quality of data of both particles and trace elements in seawater at the same time in lots of different places in the ocean that we can now start to really examine these ideas systematically and quantitatively. So that's the story I will tell you today. So first I will start by telling you what marine particles are in the ocean, what their distributions are and what their composition is. And from there on, that's the work that I do in my lab. And from there on, I will talk about how we can use that information to assess scavenging in the oceans, this scavenging removal of trace elements in the ocean. And this is the work that is done with lots of colleagues and collaborators in the GEOTRACES program. So first, in order to go through that, just as an outline, I will talk about observed partition coefficients. I will talk about the kinetics of scavenging. I will tell you about the importance of particle composition for determining the affinities of different trace elements to particles. And then I'll focus very specifically on manganese oxide. It's a little bit of a spoiler as being a super important particle phase for the scavenging removal of trace elements. And then finally, I'll end with some conclusions. So what are particles in the ocean? This is a picture from Catherine's textbook in marine geochemistry. So particles in the ocean can have two sources. They can come from external to the ocean, so think continental material, lithogenic material that's blown in from wind or carried in from currents from the margins or from rivers. And so this is mostly lithogenic, so that's the external source. And then we have internal sources, and these comprise the majority of particle sources in the ocean. They are mostly produced by marine biological activity, producing particulate organic carbon, calcium carbonate, biogenic silica, but also produced by authigenic precipitation of minerals such as iron and manganese oxyhydroxides. So when we collect particles, as Catherine mentioned in her introduction, we use these in-situ pumps. And so these are battery-operated pump systems that we deploy and send into the ocean. We send a string of these down a wire so that we could collect. They're on a timer, and they just turn on. They're actually quite simple. They're just on a timer. And they turn on, and they pump for 4 hours. And through the 4 hours of pumping, we can collect thousands or hundreds to thousands or so liters of seawater. And we could collect it through these two filter holders. And so we get these filters, and here's a cartoon of a filter. They're usually sort of yellowish, greenish. The green sort of indicates the biogenic material, so that's particulate organic matter, calcium carbonate, biogenic silica. But then also some of these external particles, lithogenic particles, here indicated as blue dots, maybe some authigenic minerals, here indicated as these red dots, and then maybe any trace elements that are scavenged to the surface, here I've indicated as this very light orange coating on the particle surfaces. So our job as geochemists is we get these samples, and then we have to measure the chemical composition of these particles and interpret what it is that means for important oceanographic processes. So let me step back and sort of give you a little molecular refresher on scavenging. So if you think of a particle surface, here's a figure from Hanneman and Sanchi. The particle surface you can think of as having functional groups, and then you can think of trace elements in solution as metal with the functional groups on the surface of the particle as a ligand, and the metal may complex with the ligand and form either an inner sphere or outer sphere complex, and that is adsorption. That is the scavenging process. The more functional particle sites that you have, then the faster your adsorption will be. And of course, the different types of ligands will also affect the type of complexes you will have. And so if you think of it in that way, then if you think first, the more sites that you have, the faster your adsorption will be. Then the number of sites will be affected by the particle concentration. The more particles you have, the more surfaces you have, probably the faster your adsorption will be. But it is also affected by particle composition. Different particle types have different specific surface areas. And so, for example, oxyhydroxides have much greater specific surface areas than other particle components such as lithogenic particles, such as clays. So you can imagine that a particle assemblage that has more oxyhydroxides will have more available surface areas for the same particle mass. So the number of sites is affected by both the concentration and the composition of particles. But also the types of sites, of course, are affected by the composition of particles. If you have oxyhydroxides, that will be very different than organic carbon in the types of ligand presented to the seawater dissolved trace elements. So we need to know both particle concentration and particle composition if we are to understand the process of scavenging in the ocean. So that's what I do. In my lab, we spend a lot of effort measuring these different components. And you can, to a first or even second approximation, the particles in the ocean are made up of these 6 components. The biogenic phases are in green, so particulate organic matter, calcium carbonate, biogenic silica. Lithogenic particles are in blue, and then iron and manganese oxyhydroxides here are in red. There are, of course, other components, and depending on where you are, some of them may become quantitatively important, but these are probably account for most of the particle mass in most parts of the ocean. And then we measure all of these components in 2 size fractions of particles in order to get a sense. The size fractions are to get a sense of particle dynamics, which I won't talk about today, but that's the other half of my life. And then we add up the stoichiometric masses of all of these different particle components in order to get the suspended particulate mass. So this is the particle concentration, and then the breakdown into these different components is the particle composition. So this slide represents 15 years of work in my lab by many, many people, and is just showing you the distributions of particle mass in 4 GEOTRACES, US GEOTRACES cruises. So here's one in the North Atlantic, the GA03 cruise. The GP16 cruise was a zonal cruise in the South Pacific. The GN01 cruise was in the Arctic, and the GP15 cruise was in the Pacific. So for those who haven't seen these plots before, the y-axis is depth in the ocean. The x-axis is some sort of distance, either in kilometers or in, this one is in latitude, this one is in longitude, and then the color bar shows you the concentration of particles in the ocean. And mostly what I want you to see is that if you squint a little bit, you'll see that particles are generally higher in concentration at the surface, lower at depth, higher at the margins. So if you were to collapse all of this information onto one plot here, so here is depth on the y-axis, concentration of particles in micrograms per liter on the x-axis, you'll see that in the surface it's generally some tens of micrograms per liter, and in the deep ocean it's a few micrograms per liter. Sorry, these numbers are so small. So tens of micrograms in the surface, maybe up to 100, maybe 1,000 in some weird bottom nepheloid layers, but in general, those are the concentrations we're working with. And you see that there is a general decline with depth, as mostly particulate organic matter gets respired back to CO2. Okay, so that leads me to the particle composition, and now those 6 different particle types that I told you about, I've color-coded this way. So blue is particulate organic matter, red is opal, biogenic silica, yellow is calcium carbonate, purple is lithogenic, green is iron oxides, hydroxides, oxyhydroxides, and light blue is manganese oxide. And I've shown you now these 4 cruises for which I showed you those sections. These are the average compositions, and so on the x-axis is the fractional contribution by each of these particle types. Here's the Arctic, here's the Pacific meridional transect, the Pacific zonal transect, and the North Atlantic transect. So you'll see that particles in all ocean sections are dominated by particulate organic matter in the surface ocean. So more than 50%, so here's the 0.5, more than 50% of the particles, and on the y-axis are depth bins. So the surface depth bin is always more than half particulate organic matter. And as you go down in depth, particulate organic matter goes away. In fact, many particle components, the biogenic particle components, all pretty much decrease with depth, but particulate organic matter decreases faster, so the relative composition and the absolute composition of particulate organic matter decreases with depth. The second thing maybe to notice is that the Arctic and the North Atlantic have a lot of purple, but the Pacific does not. So the purple is lithogenic material. The Arctic is getting a lot of lithogenic material carried laterally from the margins. It's a inland closed basin, so there's a lot of margin influencing the inner basin. And then the North Atlantic is getting a lot of input from the Sahara, from atmospheric deposition. So these two basins have a lot of lithogenic material. Pacific has very little. We're mostly on the eastern side of the Pacific, so we are not getting a lot of Asian dust. Maybe a third thing to notice is there's almost no calcium carbonate in the Arctic. There's almost no opal in the North Atlantic, at least when we were there. And then iron and manganese oxyhydroxides are never quantitatively important. So these are the light green and the light blue. You don't even see it on GP15. You could just barely see it here in GP16. You can see it maybe the best here in the Arctic. Not very quantitatively important, but as I'll show you a little bit later, they still end up being very important in the end for scavenging. Okay, so that's this part done. So now that we have at least a brief overview of what the particles look like in the ocean, we can start to combine it with trace element information to understand scavenging. And this is where this part is only possible with all of my GeoTraces colleagues. Okay, so I will go through these one by one. So first, how do we assess scavenging? One of the common ways to assess the extent of scavenging is using an empirically calculated partition coefficient, KD. I'm going to call it KD obs. So the observed partition coefficient is simply the particulate TEIs, trace element and isotopes, that the trace element that you're interested in or isotope that you're interested in the particle phase, divide it by the trace element you're interested in the dissolve phase, and normalize it by how much particle mass there is. So that ends up being the particles per gram of particle mass divided by the particles per gram of seawater, and tells you how much is partitioned to the solid phase. A higher KD means that higher numerator, there is more of the trace element that's partitioned to the solid phase. So a common way to plot this data is to look at how the KD, usually in log form, varies as a function of particulate concentration, usually on the x-axis, also in log form. Since the KD, if you look at this formulation for how we calculate it, is already normalized by SPM. And the reason it's normalized by SPM is we're trying to use particle concentration as some sort of metric for the number of surface sites available. So we use that as a sort of convenient metric, because that's something that we can measure. If, in fact, particle concentration is a good metric of particle sites, then plotting the KD observed versus the concentration of SPM should give you a straight line, because the higher your concentration of particles, then the more you're normalizing it by, and it shouldn't change as a function of particle concentration. However, what we normally observe is something different. We often observe that the KD decreases. The observed partition coefficient decreases with increasing concentrations of particles. As more particles are in solution, we in fact see less partitioning than you would expect to the particle phase. And then the other thing we see is that there's usually a lot of scatter about the line, and sometimes this could be interpreted as the effect of particle composition on scavenging. Okay, so here are some data. This is data from Chris Hayes when he was in Bob Anderson's lab, and it shows you the partition coefficient, the observed KD for thorium-230 and protactinium-231 as a function of particle concentration on the x-axis. And you see basically this sort of feature that there is a decrease in the KD with particle concentration, and there's a lot of scatter around the line. So there is a particle concentration effect, this so-called particle concentration effect, and there seems to be an effect of particle composition. I'll point out that these different colors highlight particle samples that have particular compositions. So for example, the red is very high particulate organic matter, the blue is very high lithogenic particles, and the green is very high iron oxyhydroxides or manganese oxides. Okay, so here are the data, and I'm going to break it down and sort of consider these different parts. First, I'll look at the particle concentration effect. My collaborator and co-student and I decided that we wanted to look at the kinetics of scavenging. And so usually the particle concentration effect is explained as an artifact of increasing colloidal material at high particle concentration. So colloids are just nanoparticles. They're actually particles, but they pass through the filters that we use, and so operationally they get measured in the dissolved phase. So you can imagine that if you have a lot of colloids, it'll inflate the denominator and it'll make your observed partition coefficient small. And so if colloids increase with increasing SPM, you would decrease the amount of decrease the apparent partitioning of your trace element to particles. By looking at the kinetics of adsorption and desorption, we think that we might have an alternative explanation, although this is something I think that we still need to explore even further. So let me tell you a little bit about that. Okay, so you can represent the thorium cycle as a simple box model. So the activity of dissolved thorium is determined by the production from decay of its parent, by decay of itself, loss by adsorption to particles, gain from desorption from particles. And the activity of particulate thorium is then gain of adsorption, loss from desorption, loss by decay, and loss by sinking. So you could write out a mass balance for this, and then you can assume steady state because that's easier. And then you can rearrange your mass balance to derive this expression to relate basically the activity ratio of particulate to dissolved thorium, and then add in a normalization by SPM. So now you have what looks like the KD operational definition, and you can relate that to a ratio of the different rate constants that are used to describe this model. You can further make a few simplifying assumptions. You can assume that decay doesn't matter, the rates of decay don't matter. Thorium has a pretty long half-life. That sinking, maybe you make the assumption that sinking doesn't matter. Maybe that's not as good of an assumption. But in any case, we'll make those assumptions. And then we can simplify our expression here to say that the observed KD, this empirical, just what we measure in the particles over dissolved phase, normalized by particle concentration, is can be represented as the rate ratio, the ratio of the rates of adsorption to desorption, normalized by SPM. I'm going to call that capital K. So this will be a sort of kinetic explanation of adsorption and desorption, and we're going to see how that compares to the just empirical description of the partitioning of thorium and protactinium. Okay, so the observed empirical one showed a particle concentration effect. It showed an effect of particle composition. So now we'll calculate a kinetic version of this and see whether it looks the same. So to do this, this was done with my collaborator Olivier Marchal at HUI and a former student of ours, Paul Lerner. And so he took this simple thorium model that I described before, paired it with a very simple particle model, no size fraction. All this particle model does is it remineralizes and it sinks, doesn't do anything else. But by pairing these together, he was able, and applying inverse methods to observations of dissolved and particulate thorium and protactinium. No, actually not protactinium, just thorium. And actually more than just 230. We used several isotopes of thorium. He was able to estimate rates, all of these rate constants that affect the adsorption and desorption of thorium onto particles and from particles. So I'll just cut to some of the conclusions. So what he plots here is the rate constant for adsorption of thorium onto particles as a function of particle concentration. So this is just looking at the adsorption part. And he sees that the adsorption rate increases, this is the rate constant, sorry, the rate constant increases as a function of particle concentration. So that sort of makes sense. The more particles you have, the more surface sites you have, presumably that will increase the rate constant of how quickly thorium will stick onto a particle. This was less obvious. This is now the loss rate constant. It's actually the sum of desorption and remineralization because we couldn't tell the difference. So the loss of thorium from particles as a function of particle concentration, that also increased with particle concentration. That's not nearly as obvious. In many of the derivations from Honeyman, for example, they assume that there is no relationship between the loss of thorium from particles and particle concentration, and yet we see some sort of dependency. What we also see is that the dependency of the loss on particle concentration is actually slightly higher. The slope is slightly higher than the dependency on the gain on particle concentration. So if you take the ratio of them, then you end up losing thorium from particles slightly faster than gaining thorium to particles as particle concentrations go up. And so you end up with a sort of kinetic particle concentration effect as well. So what this means, we're not sure yet, but it means that the dependence of thorium loss on particle concentration was unexpected. But if it's true, then that means that we don't necessarily have to invoke colloids. It's not necessarily just an artifact of how we measure it. Maybe there's something really going on with the kinetics of how thorium scavenges onto particles and how it comes off of particles that changes as particle concentration increases. There's lots of ideas that I have about this, and we haven't tested them yet. But this is just a suggestion that we think about the kinetics also, and not just some sort of artifact of how we measure it. So it could be true. It could be real, I guess, is what I'm saying. Okay, so that's the kinetics. What I want to move on to next is to tell you about how particle composition might affect the affinity of particles to trace elements. So again, going back to Chris Hayes and Bob Anderson's observations of the thorium and the protactinium partition coefficients, you see now that I'm going to focus on the different colors here, that the particles that have sort of unique, more anomalous compositions tend to be the outliers, the ones that cause a lot of variance in our relationship here. So what Chris did is that he decided to model the observed partition coefficient just as a linear combination of n-member partition coefficients. So he took the 6 particle phases that we measured in my lab, and we know the fractions of each of these particle compositions because we gave them to him. And then he assumed that each of these different compositions were n-members, that they each had a specific n-member, what he called n-member partition coefficient, or intrinsic partition coefficient. That would be the KD with the component indicated on its superscript. And so he just did a some linear algebra to fit the best n-member coefficients based on the data that we gave him. He did this and derived, and I'll show you in the next slide, what the different n-member partition coefficients were, which then represent basically the one at least interpretation for it, even though it's just statistics. But one interpretation for the statistics is that it represents some inherent affinity of each particle type for, in this case, thorium, if he was doing it for thorium, and for protactinium. This method has been applied by many investigators, and so in the next slide, I'll show you the results of, again, lots and lots of work by lots and lots of people in one graph, and that's here. Okay, so what I have here is on the y-axis is the partition coefficients, the sort of n-member partition coefficients. Each of the colors is for the different particle phases, the 6 different particle phases. And each grouping is for a different element or isotope. And so here are Chris's original results for thorium and protactinium. Here are results for mercury from Carl Lamborg. Here are results for polonium-210 and lead-210 from Yitong and Gillian Stewart's lab. And each of these colors, again, represents the n-member affinity partition coefficients for each of these phases. So a few things to point out. There's a lot of data here. But one, you never see any orange. So opal is never a significant phase for scavenging of thorium or any of these elements or isotopes. But recall, opal is low in the North Atlantic. So we're still, the US GEOTRACES program has, for some reason, sampled almost all low opal regions. So we have a high opal region that we just sampled, so stay tuned. But at least in the North Atlantic, opal is not an important phase at all. The next thing to notice is that iron and manganese oxyhydroxides, so the green and the blue bars here, have so this is a log scale. have 1 to 2 orders of magnitude higher affinity for all of these elements. These are very different elements: thorium, protactinium, mercury, polonium, lead. Always higher for manganese and iron oxyhydroxides. So, hearkening back to both Ed Goldberg and to Carl Tarikian, why are these oxyhydroxide components so effective at scavenging trace elements from solution? As I mentioned before, oxyhydroxides have very high surface area, therefore lots of surface sites. So that's certainly one reason. 2, they may have other properties that make them effective scavengers. So first, I'm going to think about surface area. So what I'm showing you here are the 6 particle components I've talked about, SEM images that I didn't take, that I found on the internet. So organic matter, calcium carbonate, clays, opal, manganese, and iron. The scale bars aren't all the same, but there's sort of a range from lowest specific surface area to highest specific surface area, sort of in this direction. So it goes from 1 meter squared per gram, which is the organic matter, to 250 meters squared per gram, which is both the manganese oxide and the iron oxides. So those can be even higher. It could be even many hundreds of meters squared per gram. And then clays are sort of in between, calcium carbonate and is about 10, clay is about 40, opal about 100. So this is 3 orders of magnitude, 1, 2, 3, yes. 3 orders of magnitude of specific surface area. So you can imagine that the fractional weight of contribution is not actually representative of how many surface sites they have to offer to trace elements in solution. So my former student Yang Xiang decided to actually take this on and correct for the effective surface area. So on the left-hand column are the original data. So looking at the observed thorium-230 partitioning, the observed protactinium partitioning as a function of particle concentration. And you see that it's quite scattered. You would expect the partitioning would increase sort of, I don't know, coherently as you increase in particle concentration, but there's clearly a ton of scatter. Now, if instead of particle concentration as a metric of surface sites, you now incorporate explicitly how much surface area each of those components have, and we know how much each component there is, and you plot the partitioning against the total surface area, you now see much nicer relationships between how much partitioning you have versus the total surface area available from your particles. So that's cool. Yang decided to recalculate the intrinsic M-member partition coefficients. So this is the original. So on the x-axis is the observed KD, so this is just what's measured. On the y-axis is the reconstructed thorium KD and protactinium KD using that original N-member linear combination, using concentrations of particles as your metric. And it's quite tight, but the slope is not good. So the dashed line is the one-to-one line, and you could see that it overpredicts at low concentrations and underpredicts at high concentrations. Now, if instead of using particle concentration, you now recalculate the N-member coefficients with the surface area, you get a much nicer relationship. Okay, so what are those new coefficients now? I apologize, this is now in a different order as I showed before. But the blue bars now are the N-member thorium coefficients for the different particle phases calculated the original way and showing 1 to 2 orders of magnitude of affinity for, say, manganese oxide is about 2 orders of magnitude more higher affinity to thorium than calcium carbonate. The orange bars are the recalculated N-member coefficients if you use surface area. So basically what you're doing is you're eliminating the effective surface area from the different particle components. And what I want you to notice is now the bars are almost all the same across the different particle components. So what that means is that the particle composition effect for thorium is a surface area effect. If you take into account surface area, you eliminate the variation in affinity to the different particle components. Okay, cool, we figured it out. Doesn't work for protactinium. So protactinium, blue is the original data, orange is the recalculated data with specific surface area. And now the specific surface area orange bars, you still see quite a lot of variation. You still see a couple of orders of magnitude difference between, say, calcium carbonate and manganese oxide. It might have slightly shrunk the variability between the different components, so there was a slight surface area component, but it's telling you that surface area isn't the whole story, that the nature of the particle surfaces, probably the functional groups, the surface charge, the types of complexes it makes with protactinium, for the different particle components matters for protactinium, but not for thorium. Okay, so we're not going to solve that question, but that sort of made us think, oh my gosh, so interesting. Let's see whether we can understand what the nature of manganese might be. So given that manganese oxide still ends up being the most efficient component for all trace elements, we wanted to look deeper at what about the nature of manganese oxide might be different. So we're going to do before I do that, just briefly, in general, surface charge of particle components matters. So here is the charge of a surface for oxyhydroxide as a function of pH. And what this is showing you is that the point of 0 pH, 0 point charge, is about pH 8 for iron oxyhydroxides, which is about the pH of seawater. So what that means is that iron oxyhydroxides are generally neutral to slightly positive to slightly negative, depending on where you are in seawater. And so it can scavenge a variety of different types of trace elements and isotopes. Manganese oxides has a very low point of 0 charge, which is to say that all of seawater is going to be up here, which means that the particle surfaces of manganese oxides will always be negative. So it will be not good at attracting negatively charged ions, but quite good at attracting positively charged ions. So that's one difference between these two. We wanted to use the hydrothermal plume of the East Pacific Rise as a case study because this is where we have very high particulate manganese and particulate iron, manganese oxides and iron oxyhydroxides. It's hard to do this anywhere else in the ocean because the concentrations are just too low. This is the only place where they're high enough that we can use techniques like synchrotron X-ray absorption spectroscopy. So this work was led by a research scientist in my lab, Dr. Jongmi Lee, and she decided to look at the association of different trace elements with manganese and iron. So here is, and I will break down the examination of this into the near field, so right above the East Pacific Rise, right above the vent. Those are the near field sites, and then the far field sites are, the vent would come out here and then spread downstream, so the far field sites are downstream. So the near field sites here, this is plotting the particulate cobalt versus the particulate manganese, and we see this beautiful correlation. Particulate cobalt and manganese, very well correlated, so clearly there's some association here. Whoops. If you go to the far field plume, correlation completely dies away. It's not there. This is in the small size fraction, this is in the large size fraction. It looks like they make a line, but these are different particle pools. So within each size fraction, there is no correlation between manganese and cobalt. If you look at molybdenum, in the near field, beautiful correlation in the large and in the small size fraction. In the far field plume, no relationship at all. So what we wanted, so this just summarizes our observations. I didn't talk about the size fractionation, but the size partitioning of manganese was very weird. There was a lot of large particles in the near field plume. We saw these strong correlations. Normal size fraction in the far field plume, and no correlations. So we wanted to use this as sort of a test. Is there something about the mineralogy of the manganese oxide that's different in the near field and far field plume that would affect the scavenging of these trace elements? So what's plotted here in the white are particulate manganese concentrations, so depth on this axis. This is just focusing on the hydrothermal plume depths, concentrations up here. And then the bars are the manganese redox speciation of the particulate phase. Anything in blue is manganese 4, in green, manganese 3, in red, manganese 2. Mostly what I want you to notice is that in the near field plume, you see significant green. You see significant presence of manganese 3 in the particulate manganese. In the far field plume, you see much less. Manganese 3 is much smaller there. So we found this beautiful paper out of Colleen Hensel's lab in which they synthesized biogenic manganese oxides, and then they aged it and looked at how its mineralogy changed as it aged. And when it was first formed, it was this manganese 4 hexagonal symmetry, very reactive bernesite, mostly MnO2, manganese 4 MnO2. And this is the X-ray absorption spectrum soon after it was formed, and you see this peak. And then over a few days, what they saw was a lot of surface reaction from dissolved manganese 2 that was reacting with the surface of the manganese 4 oxide, incorporating it into incorporating manganese 3 into the lattice of the actual mineral, and you see the decrease of this peak. So you see the ripening led to less reactivity into a different type of symmetry, triclinic symmetry, and a much more manganese 3 in the mineral. Also, another paper from Tanaka showed that this process could happen for cobalt too. So cobalt can compete with manganese in order to incorporate the cobalt 3 into the lattice of the manganese oxide. And so for us, that seemed to make total sense. So what we think was going on is we see this manganese, I forgot to show you the data, but I have it afterwards if you don't believe me. We saw this triclinic form, this ripened, less reactive manganese oxide in the near field only, and an abundant manganese 3. So this seemed to suggest that process, that we had rapid manganese, microbial oxidation of manganese that was very reactive. It reacted with cobalt to form these manganese 3 and cobalt 3 oxides. And because it was so reactive, these manganese particles grew and got very big and sank and didn't make it out into the far field. So the only stuff that made it out into the far field was the less reactive stuff, the stuff that didn't react with cobalt, that didn't react with itself, so it didn't aggregate and leave the solution. And so that's the non-reactive stuff that got transported out into the far field and no longer scavenged cobalt or molybdenum. So just as a quick summary, we found differences in the reactivities of the manganese oxide in the near field and the far field that seem to be related to the scavenging of trace metals, cobalt and molybdenum. There's a really interesting protactinium story too that also is consistent with what I was just telling you, but it takes too long to explain. So it seems to apply to other trace elements too. So just to summarize, GeoTraces has enabled high-quality particle and trace element and isotope data that allow us to further probe the mechanisms of scavenging. I've shown you that the particle concentration effect that has been observed for decades may have a kinetic explanation, although we don't quite understand that yet, so it's something definitely to study. Goldberg and Tarikian were right. Iron oxides and manganese oxides do reign supreme in removing cations from seawater, and we understand why a little bit better, and it's not the same explanation for all trace elements and isotopes. So for some TEIs, such as thorium, the high apparent affinities of iron hydroxide and manganese oxides are purely to do with this higher surface areas, but for others, such as protactinium, the surface area correction only explains a very small proportion, and the nature of these particle surfaces matter more. And as a case study, we looked at the East Pacific Rise hydrothermal plume, and we found that atomic scale differences in the manganese oxide mineralogy affected the reactivity and therefore the scavenging of trace elements like cobalt and manganese over hundreds of kilometers. So this manganese mineralogy case study illustrates that not all manganese oxide is the same. This is likely true for the other particle components that I talked about. So particulate organic matter is a very broad box. It's probably not the same everywhere you go. The surface organic matter is probably not the same as the deep organic matter. Calcium carbonate might be different if it's produced by different organisms. So is there a better way to classify particle composition and type? This is something I spent a lot of time thinking about, and I don't have an answer for yet. If you do, please let me know. Nonetheless, even these relatively crude particle characterizations and sort of categorizations allow us to make headway into understanding some of the mechanisms that are affecting the scavenging of trace elements from seawater. Thank you very much.
Thank you, Phoebe. We are starting the Q&A session, but before that, I just want to do a short announcement to the people, the delegates who registered for the plenary lunch. You are welcome to gather at the bottom of the stage, so we will go together to the room 4, where this is supposed to happen. So don't forget, and if you wish, you can gather there. At the end of the Q&A session, we will go there together. Okay, so as we said yesterday too, the microphone they are at the bottom and at the top of the stair. So if you have questions, this is on both sides here. Please, you are welcome. Nothing. It's always a moment of... and we don't see the hands, actually. Ah, no.
Hi, Phoebe. Thanks very much. That
Hi,
was
Susan.
great. This might be a stupid question, but molybdenum is molybdate anion.
I know,
So I've
confusing.
never understood why it absorbs on manganese oxides.
Right, me neither. So I went back, there's a paper I can point you to. Remind me, send me an email and I'll send it to you, in which they talk about, they did experiments and they showed that the molybdenum isotope fractionation relates to the degree of inner sphere complexation. So I think oftentimes the electrostatic complexes are outer sphere, but once you're in inner sphere complex, it sort of goes beyond electrostatics. And so somehow it seems like it pulls the molybdenum out of the anion. I'm not completely sure, but it forms the molybdenum adsorption is an inner sphere complex. So I think that's why. It confuses me too.
Thanks for the nice talk. I just wonder that when you pull together your KD calculation from 6 different kind of particles, you use the fraction. I wonder why don't you use the absolute quantity of each different kind of particles instead?
Yeah, the KD is itself a fraction of the total particle concentration, and so that's why we use the fraction of composition. But actually, we repeated the same kind of exercise with the rate constants, which is not a fraction, and for that we used just the concentrations.
Phoebe, thank you so much. What a great talk. And so as an organic matter person, I'm just wondering, you said you don't really know, but is anyone looking at the organic matter composition in these studies or anything? Or do we have anywhere to start?
Not in GEOTRACES.
Okay.
But this is something that I'm super interested in, and I need to talk to organic geochemists to figure out what I'd love to know is what is the best metric for labelity, whatever that means. So in my biological pump life, I want to know about how quickly things are mineralized. In my scavenging life, I want to know about how reactive they are in forming complexes. And I don't know what to measure, what one would measure. So if you have ideas, I would love
to talk to you later.
Great.
Hi, thanks for the great talk. So you mentioned that the manganese oxide is a very important scavenger for many trace metals. But as also the manganese oxide is quite low in concentration in the ocean. So to make it a dominant scavenger for a specific trace metal, do you have any rough idea that how much higher the manganese oxide KD should be to make it the dominant scavenger?
It sort of works. So the KD is 1 to 2 orders of magnitude higher, and its concentration is usually 2 orders of magnitude lower. So it doesn't end up explaining all of the scavenging, but it ends up explaining more than you'd expect from its concentration because its KD is 1 to 2 orders of magnitude higher. So it basically inflates its concentration by that much, and it does end up sort of working out.
So if it's like 1 or 2 orders of magnitude higher, then that could be comparable to POM or other.
Yeah, exactly.
Okay, yeah, thanks.
Yeah. Mm-hmm.
We have a remote question, so may I ask it? Okay. Are there nonlinear absorption models attempting to understand the partitioning?
Good question. Whenever I go to the soil literature a lot to try to understand sorption because that's where a lot of that work is done, but the concentrations in the ocean are so low that it's really hard to actually do these experiments. You can do them at higher concentrations, but they may not actually be reflective of what's going on in the ocean. So I'm going to put a bookmark on your question and not answer it, and I don't know.
Welcome.
Hi, thank you very much. I'm not very into all these organic compounds. I'm more like a general geologist, but there is a good record of manganese nodules in the geological history in pelagic sediments.
Yeah.
Could this be applicable to
Yeah.
that, or the scale of the process is lost in somewhere?
No, that's a great question. So that first paper I told you about, the 1954 paper from Ed Goldberg, he sort of postulated that these iron and manganese oxides mattered, but he couldn't measure them, and so he exactly went to the manganese nodules in order to, as a case study for how these trace elements interact with manganese and iron oxides. I think it's absolutely a good model, but slightly different because manganese nodules are also affected by the sort of diagenesis of trace elements coming from the sediments. So that's going to change the relative concentrations, and so it may not be reflective of what's going on in the water column. But it certainly is a model for what's going on in the ocean, just at different conditions. But it is a good model.
So if knowing the diagenesis evolution of some rocks based on other minerals, we could just make a reconstruction of the nodules, of the trace elements found in the nodules?
Yeah, we could, but it won't tell us about what's going on in the water column. Yeah.
Thank you very much.
Thank you so much for your talk. Is there anyone on GeoTraces looking at the microbes that might be bound, and do you think the microbes might affect the adsorption of trace elements?
Sort of, yes. So we have what we call biogeotraces, which is on some cruises we try to invite people to take measurements for genomics or proteomics or metabolomics or various omics and so some people have looked at the presence of certain types of bacteria for, in different samples. I think so far, as far as it's relevant to me, is that I've thought about so far, is mostly at these sort of biogenic, biologically mediated mineral precipitations, like manganese oxide. It's thermodynamically favorable to precipitate it, but it's actually kinetically inhibited, so you need a microbe to do it. And so without a microbe, you can't make manganese oxide pretty much. And so for that, the microbes have this sort of indirect role at making the mineral that then does the scavenging. In terms of actively mediating the scavenging, I would say probably also indirectly through the production of, say, extracellular polysaccharides or something that might affect the scavenging.
Okay, thank you.
And thanks for your talk. I have one point. So I'm curious about the special surface area of the one kind of particle, such as ferrihydride. You know, the ocean particle is a mixture. I mean, that's how did you get the exact data of the special surface area? Yeah.
Those are just literature values. So we just looked at the literature for different types of ferrihydrites, and that is sort of a rough average. It's not the highest number, it's not the lowest number. So there's definite room for improvement there.
Okay.
Yeah.
Thanks.
Hello, thanks a lot for the nice talk. Actually, I have 3 questions.
Great.
The first one is, you raised the question what to do with the same mineral net composition has different crystal phases and different reactivity. I wonder whether Raman microspectroscopy could be an answer to that. The second question was that there's much interest in microplastics in the ocean, so you sample a lot of particles. Have you got any insight on that, and how many plastic particles would be there per total particles? And the third question is, I liked it how you removed the artifacts out of your second data set by normalizing to this total surface area rather than the particle concentration. And I wonder whether this could also be the solution to your first data set, where you had this kind of intriguing correlation with particle concentration, and there could be the possibility that particles rather aggregate if particle concentrations are higher, that you have larger particles with a smaller surface area, and so on. So
Yeah. Okay, first one, Raman. Yes, I have a colleague with Raman, and I keep on wanting to talk to her about using it. 2, plastics. Unfortunately, any plastics would show up as particulate organic material because I just burn it, and whatever comes out is that.
So that would be a case for Raman too.
Oh, yeah. But I do know that some people have tried specifically to look for plastics I think microscopically, and look for changes in partition coefficient. Like I have mercury colleagues who have tried to do that. And I think in some cases it was interesting that it might have had more of an effect for mercury, but I can't remember. So maybe. 4 was, oh yes, size spectrum. So right now we only have very crude size partitioning between small and large. I would love to get some better representation of the particle size spectrum so that we could take that into account. We haven't done that because our particle, our size partitioning is too crude, but absolutely we would love to take that into account. Thanks.
Our last question, but I have a remote one. May I take the remote one? Okay. So Pablo Paston asks, how do you consider hydrodynamic and ocean currents in interpreting your results?
Usually we ignore it. Not because it's not there, but because it's hard to deal with. Okay, no, that's not true. I have a better answer. We did look, well, yes. We choose our stations carefully so that we can ignore it because it's too complicated. But we also, Paul and Olivier did look at the effect of the deep water boundary currents and looking at the relative importance of transport versus adsorption and desorption. So we can look at that in special cases. I personally have not done that very much because it's too complicated.
Okay, thank you.
A very short question, how the temperature can influence the absorption rate of the elements?
That's interesting. I haven't thought about temperature very much. I presume that it would increase the absorption rate. Most of the deep ocean is not that different in temperature, although I guess that's not true. There are temperature gradients.
Because you have a Pacific section and the temperature between surface and the deep ocean could be as high as 20 degrees. So perhaps I'm wondering if you consider the temperature effect can the prediction better.
We haven't looked at it. I'll think about it. Thank you.
Thank you. That was not the last question. Surprise. So Sourav Ganguly is asking, transmitter stable isotope ratios could be a good tracer for better characterizing particulate composition, specifically relationship between stable isotopes and KD. Is there anyone working in this line? Good answer. That might be useful.
Yeah. My other students working on cadmium, and we think that there is definitely an interplay. It's not actually adsorption, though. Interplay between the stable isotope composition of cadmium and how it gets taken into the particle phase. The molybdenum example that I gave before, that was a very nice and specific example on how adsorption, inner sphere versus outer sphere, could be correlated to isotopic composition differences. I think part of the challenge is that at least the experimental stuff has to be done at higher concentrations. So in the ocean, we have, of course, measurements that span gradients, and that's our main tool for trying to probe the effect of these processes on each other. So, yeah. Definitely an interesting thing to keep in mind.
So the last one is from Bob Anderson.
Oh, good.
Hi, Bob. In session 1301 this morning, several talks pointed out that Birnesi transformation to dodorokite affects nickel absorption. Could this be a factor in the GP16 hydrothermal plume results that you showed? Would the synchrotron data show this transformation?
Yeah, it should. I don't think we saw todorokite. We saw bernesite, hexagonal symmetry, and triclinic. Doesn't mean it doesn't exist, but we were right at the limit of our detection, even in the near field. We couldn't do it in the far field. So it might exist, and that's the sort of thing that you could examine, let's say, in a manganese nodule quite easily, but very difficult to do in suspended particulate matter. So we didn't see it, but it doesn't mean that it's not there.
Thank you. Thank you, Bob, too. I think we are done. I again invite the people who want to meet Phoebe and ask more questions and have a discussion with her. Please join us here, and we will go to round 4 on level 1, if I'm right, in the B building. A building. In the A building, not in the B building. Okay, so
great. Thank you for your questions.
Please come here.